In this lecture, we will discuss about the Nyquist stability criteria. So before going to discuss about the Nyquist stability criteria, some of the features of the Nyquist stability criteria or Nyquist criteria I will discuss here. First of all, here, say for example, your open loop transfer function of any system is normally denoted by GSHS, and if you consider the unity feedback system, that HS is equal to 1 for unity feedback system. Now GSHS is your open loop transfer function. From the open loop transfer function, that means frequency response of open loop transfer function we get by using the polar plot, and from the frequency response analysis we can get the stability of closed loop system. So what is the closed loop system corresponding to the GSHS open loop system? Say this is your fundamental block diagram of any control system. So this is your GS. Now this is your output RS, and here you will get the feedback part HS. So the closed loop transfer function CLTF, that is equal to CS by RS equal to GS by 1 plus GS into HS. Now this is the most important term. That means this is known as the characteristic equation. You all know it. Now from the characteristic equation, what we get? We get the roots of the system. And finally, by using the Nyquist criteria, whatever actually we get from the frequency response of open loop transfer function GSHS, we can get the relationship between this frequency response of the open loop transfer function and the roots of this characteristic equation. That means all the poles and zeros of 1 plus GSHS equal to 0. All the poles and zeros of this characteristic equation 1 plus GSHS is equal to 0 will be related with the frequency response of the open loop transfer function GSHS by using the Nyquist criteria. And by using this Nyquist criteria, we can get the stability of the any system. We are having three quantities like 1 plus GSHS equal to 0. This is your characteristic equation. From this you can get the number of zeros at the right hand side of a plane, and P is the number of poles at right hand side of S plane. That means if you know this number of the zeros at the right hand side of the S plane and number of poles at the right hand side of the S plane, both are related to 1 plus GSHS, and you know the frequency response of this transfer function GSHS, then there is a relation which is known as conformal mapping. By using this conformal mapping, we can relate the stability of the system, and we get, say for example, GSHS equal to 1 by 1 plus 2s. This is a type 0 system, and this is the open loop transfer function. Now corresponding to that, you get the characteristic equation 1 plus GSHS equal to 1 plus 1 by 1 plus 2s equal to 1 plus 2s plus 1 by 1 plus 2s. So we get 2 plus 2s by 1 plus 2s. So you see there are two things. One is that the GSHS is having the poles. What is the pole? This total number of pole at GSHS. So pole of GSHS, we may write it is equal to P equal to 1, and the position is at S is equal to minus half. Now this is the position of the pole, and there is a single pole of GSHS. Similarly, from this 1 plus GSHS, that is equal to 2 plus 2s by 1 plus 2s. From there you get this is the pole position. So similarly, you get the pole of 1 plus GSHS equal to same P, and that is also at S is equal to minus half. That means what is the conclusion out of there? You get the number of poles of open loop system is same and the position as same as that of the number of pole of the closed loop system, right? So there is no confusion regarding this, and from the open loop system transfer function you can get the total number of poles of the closed loop system. First of all, Nyquist criteria was to get the frequency response of GSHS, that is done with the help of J omega H J omega. That means by using the polar plot, you can get it. And number of poles P, that can be obtained from this GSHS also. So in case of 1 plus GSHS, that means that is for closed loop system, we can get P from the open loop transfer function and frequency response analysis. So what is unknown to us? Unknown to us is Z, that is number of zeros at right hand side of S plane. Now this 0 Z can be obtained by using the rules of conformal mapping. Now we start drawing the Nyquist Nyquist plot for the system GSHS equal to 1 by 1 plus 2S. So to draw the Nyquist plot for this system, first of all, what you have to do, you have to just draw one Nyquist contour. So Nyquist contour is like this. This is your real axis, this is your imaginary axis. That means this can be denoted by sigma and it is denoted by J omega. And as we know, this is your S plane, so S is equal to sigma plus J omega. This is your S plane. Now the Nyquist contour is designed in such a way such that you see, if you vary the value of S along this line, say this is your starting point. So here this is frequency axis, you know, this is real axis and this is the omega axis. Now if you can vary the values of S from say 0 to plus of J infinity. See what I've just now I've discussed. If you vary the frequency varies means the omega is varied from 0 to infinite. 0 to infinite frequency is varied. That means if you put S is equal to J omega, so S is equal to J omega axis, that means the real value at every point on this S is equal to J omega axis is equal to 0. So everywhere you find the sigma is 0. So this line, this imaginary axis is having the equation S is equal to J omega. Now if omega is varied from 0 to infinite, that means from say 0 O to certain point A, and A is some at a very large distance, say for example, so this can be taken as infinite point, and 0 to A, once this point, or if you move along the S plane, this is your S plane and you are moving from 0 to A. So what happens, corresponding to that, actually omega is varied from 0 to infinite, and if omega is varied from 0 to infinite, corresponding to that you get the polar plot of this transfer function. You get the polar plot. So when you move from O to A, you get this is your real axis, this is your imaginary axis. Now, so 0 O to A, this point means frequencies varies to 0 to infinite. That means you are getting the corresponding polar plot. So polar plot for this type of system already we have discussed. This is your polar plot. So this is also this is actually the S plane, and we are going to discuss about the Nyquist criteria with the help of Nyquist plot. So this is your S plane corresponding to, this is your J omega plane, right? This is GS HS plane, and here we are going to discuss about the conformal mapping theory. What is that? That is, see, 0 to infinite omega is varied. That means in the S plane you are varying the frequency corresponding to that. For each of the S, this J omega and H omega is varying because there is a function, it is a function of S. Now once this is varying, you are getting the polar plot. And see, 0 to B point, or in other word you can say from B to 0, from B to 0, right? From B to 0 means this is your 0 and this is minus j of infinity, because this is the negative omega axis or negative imaginary axis. So from B to O, that means omega varies from minus infinity to 0, right? If omega is varied from minus omega to 0, see here, if you put the value of omega is equal to 0, you get S is equal to 0. This is your origin. And omega is equal to infinite, that means S is equal to plus j infinity, this point. And omega is equal to minus infinity, that means S is equal to minus j omega. Or see, now this is your GSHS 1 by 1 plus 2S. Whenever we have in the previous classes discussed the polar plot, what we have discussed, how to get the polar plot corresponding to the change of frequency from 0 to infinity. And in that case, what we have done, we have actually done G j omega into H j omega. That means everywhere you have put S is equal to j omega. Now in order to get the polar plot corresponding to the frequency omega is equal to minus infinity to 0, if you put S is equal to minus j omega, if you put S is equal to minus j omega at GS HS, so you get the same polar plot but just the mirror image of the previous one, mirror image of the previous one with respect to the real axis. That means if this is the polar plot when the frequency is varied from, what is this, 0 to omega is equal to infinity. Now if you vary the frequency from minus infinity to 0, the same will be there and this will be your mirror image, right? And this point will be omega is equal to minus infinity for the upper part, and this point is equal to omega is equal to 0, right? So if you start from this point B, so B to O, O to A, this is along the imaginary axis, and the point corresponding to these are mapped like, this is your B. When you move to O, so you move to O, this is your O point. Now from O to A, you move from O to this point. That means omega is equal to 0 to omega is equal to infinity. So you get a closed path. You get a closed path in a single direction. See, from here, if you can start from in clockwise direction, you move to there. In the same direction, you come here also. So what happens, along the imaginary axis, starting from B to A through the point O, where the value of S is equal to 0. What is the value? Here the value of S is equal to 0. This is the origin. So corresponding to that, what you get, the frequency response. So once the omega is varied from say minus infinity to plus infinity. That means the complete range of frequency. Minus infinity to plus infinity, when you vary, corresponding to that you get the polar plot like this. So ultimately that is the benefit of doing the polar plot. If you know how to draw the polar plot corresponding to any open loop system transfer function, then you have to just take the mirror image of the polar plot with respect to the real axis to get a closed path, and this path is known as contour. This is known as contour. So if I write the two figures side by side, then it will be better to make you understand. GSHS, that is 1 by 1 plus 2s. This is the type 0 system. Type 0 system, and see, this is our O point, this is B equivalent to minus j infinity, and this is your point A equivalent to plus j infinity, right? So you are moving from this point, that means B to O to A, and corresponding to that we are getting, if this is taken as S plane and we are varying the fixed plane, and as you know S is equal to j omega, so if you vary the frequency omega, automatically the value of S is varied. So once the value of S is varied, that means if the omega is varied from minus infinity to infinity, corresponding to that, definitely according to this expression, the value of S is varied. Once the value of S is varied, you see, put the value of S here, and for different frequency you are varying this overall transfer function, because you put g j omega h j omega equal to 1 by 1 plus 2 j omega, right? So actually if you vary the frequency, you are varying the frequency response of g j omega, and we may call it, this plane is GSHS plane, right? And what you get till now, till the discussion, we get this is your plot, right? This is a closed contour corresponding to the this part. Now actually to find out whether what we have to find out, whether all the poles and zeros of 1 plus GSHS is enclosed at the right hand side of the S plane. That means if all the poles or zeros are lying at the left hand side of the place plane or right hand side of the place plane. So what Nyquist have done, Nyquist have considered the total right hand side of the S plane like this. So this is the total right hand side of the S plane. That means if all the poles and zeros can be considered which are residing on the right hand side of the S plane, then the stability can be achieved. So what to do in that case, if you just consider the complete right hand side like a semicircle, right? So if this is a semicircle, you see this semicircle, that means that is also the function of S, and the equation of S here you can write like this. Say this is R. So we are considering the semicircle having the radius R, right? And everywhere on the semicircle the radius remains same everywhere, as this is a circular path, so the radius is same. And if you can make the value of R tends to infinity, so you can just extend this radius to the infinite, and it covers all the poles and zeros at the right hand side of the S plane. So starting from this B to O to A, and finally it goes to, say for example, C, and coming back to B. So this contour in the S plane means it is covering all the poles and zeros at the right hand side of the S plane, right? Now how to express this expression, or how to get the expression of this semicircular path? See, this is the radius, and the radius remains same in all these points. Now coming to the Phasor concept. What is the concept of it? Say R, and you say this is angle phi. So this can be treated as one phasor, and expression of S for the semicircular indent is equal to, taken as S is equal to limit R tends to infinity R e to the power j phi. What is this? This means r e to the power j phi is the phasor corresponding to the semicircular path. You see, this e to the power j phi means the phase of this path is phi. This is nothing but limit r tends to infinity. You can write it r phi, that means magnitude and phase. So magnitude is r, that is constant, and if you put the limit over there, r tends to infinity, then this semicircular path can be extended up to the infinity. So you get the total right hand side path. And the phi means the phase. So here phase is some certain angle. If you vary this phase, here you get the radius is r and the phi is defines from the previous phi. Similarly, if you go there, the phi will be changed. So ultimately, when you are moving in the S plane, this is your S plane, that is along the Nyquist contour, minus infinity to 0 to plus g infinity, and here you see this is your actually 90-degree axis, plus 90-degree axis. Now the when this point of the semicircular path you consider, the radius will be r, and what is the angle in that case? Angle is equal to 90 degree. Now you move in this direction. As we are moving in the clockwise direction, the angle are negative, and where you reach this value c, at the c the radius is r and angle is 0 degree. Similarly, you move to this position b, so the radius remains same r and the angle is minus 90 degree. So actually, when you express this semicircular path by the expression s is equal to limit r tends to infinity r e to the power j phi, basically this phi varies from minus 90 degree, this point, sorry, plus 90 degree, as this is moving in the clockwise direction, so plus 90 degree to c, that is 0 degree, to b, that is minus 90 degree. So this is the total expression for this semicircular path. Now this is your Nyquist contour, and you get the expression for the S for this path, and this is the expression for S from B to A. Expression for S is equal to j omega. Right, now for B to A we get the corresponding GSHS contour. This is your GSHS. So GSHS contour is obtained. Now what about this part? This part is if you put S is equal to limit r tends to infinity to the power j phi in the expression GSHS equal to 1 by 1 plus 2s. So what we'll get? So GSHS will be equal to 1 by 1 plus, say, limit r tends to infinity 2 into r e to the power j phi, right? So in the denominator total phase is equal to phi. The total phase is phi because there is no other term. This is e to the power j0, so the total phase is phi. In the numerator, total phase is equal to 0. So total phase of this system is equal to 0 minus phi, that is minus phi, right? And if you calculate this expression, then so GSHS, this term limit r to infinity, you put here, you get GSHS equal to 1 by 1 plus r tends to infinity, that means limit r tends to infinity 2 into r, so 2 into infinity, so 2 into infinity is equal to 1 by 1 plus infinity, that means 1 by infinity equal to 0. So this contour, that means once you vary the value of s from this point to this point, from A to B, this contour part, that means which actually encloses the complete right hand side of the S plane, that maps to 0, right? If the value of r is equal to infinity. So this maps to 0 means this part maps to this point. So ultimately the total contour becomes similar to that of the previous drawn contour. So the total Nyquist contour is this, and corresponding to that, if the system is like this type 0, then this for this type 0 first order system, you get the polar plot is this, and as you see, this part is having the mirror image of this part, so this is your mirror image for the polar plot, so this makes you a closed path. And you get this is the magnitude 0 when the value of r is equal to infinity. Now what about phase? See, the phase of this system GSHS, so phase of this system GSHS is equal to minus of 5, and in case of S, the actual value of in the S plane, what is the phase? The value of phase varies from plus 90 degree to 0 degree to minus 90 degree, right? So 90 degree to 0 to minus 90 degree. So corresponding to that, when the value of S varies from this position to this position to this position, so corresponding to that, the phase of the overall system GSHS varies according to minus of 5. That means when the value of phi is equal to 90 degree, so this will be minus 90 degree. When the value of phi is equal to 0, in case of S, you get this is 0 degree, and when the value of S is equal to minus 90 degree, you get plus 90 degree. This is the variation of the phase. So once the magnitude is 0, so there is no such importance of changing this phase. So actually this is the calculation how you have to change the phase of the system, that is here 90 degree, here minus 90 degree, here 0 degree. So ultimately this is your closed contour. So this is your Nyquist contour and this is your GSHS contour corresponding to that Nyquist contour.